can say, has had a fresh start here, so it is a very new institute. We are building it up here, and we've changed a number of things. One of the things that is new is these programs, like the one that you are participating in. Data has always had a lot of emphasis on collaborative efforts and bringing in visitors, but we're doing this in a much more systematic way now with these programs. So these are typically, as the current one, 1 month, maybe slightly longer or slightly shorter, and bring together like-minded people who are interested in similar things, hopefully with good results. Now the institute itself is fairly small. We have 4 senior faculty if we count the ones who are still in Copenhagen. We have 5 assistant professors and about 10 postdocs. And then although we don't have any educational program here formally, our faculty are advising 7 or 8 PhD students, either the local universities or other Nordic universities. So that's a relatively small institute, but of course we are conveniently located very nearby major universities here. So I think we can take advantage of that, and if you look at the range of subjects that are studied here, that's actually, I would say, quite broad considering the numbers of people that we actually have. I think you're all in good hands here. Eddie is a local here who knows his way around, and Anders and Hans, of course, also. So I don't think I will keep you longer. I just want to, again, bid you all welcome and wish you a very successful program.
Okay, thank you. Off the water, important things to be done. So I'll just mention a few practical issues before switching to the first talk of the program, and it will be short. So this is probably something which you all think is important. The ideal way to just connect here to the internet is just by using the cable which is on your desk. And if you're with the cable online, you can also print. If you want to sit outside or in one of the other rooms and you want to have internet, there's Laila, the secretary, who you've all seen or will see soon. She has some codes with guest accounts and passwords, and apparently somebody had a problem with this morning, but we'll figure that out. Then you go to this website, and there's 3 boxes to log in, and you need to go to the middle one and put in the information. So that's internet access. For those who don't brought a computer with them, there will be a few laptops available for people to use. They're Macs, and they will be ready tomorrow, I've been told. So you can ask me or Hans, not Hans Hansen, but Hans, the computer guy, if you want one of those. Other stuff, we plan to meet, to sort of get together at 10 o'clock for coffee, so we meet each other at the beginning of the day. These rooms here, when we don't have talks, please use them for discussions and collaborations and things like that, and also the blackboards, of course. There's some benches outside if the weather is nice. Just grab a blackboard and put it outside and use it there if you wish. And we'll also have some social activities, and the first one this week will be a reception on Wednesday. It will just be here in the area. You won't miss it. One of the things we would like to do is, if there's a paper coming out of the research here, Vita has a whole list of preprint numbers, so just contact one of us to get some more information, and we'll tell you about that, so you can track a little bit of the scientific output. And talks, we'll put the slides available, and there in the corner there's a video camera hiding which will record everything, so we'll put that online as well. And that will probably be a few days before it's online, but I'll notify people about that. So I'm not sure if I forgot anything. Lunches and things like that, there's all kinds of information about lunch places on the program website, and we'll just gather people to either go to the place we were today, or you because it was not such a big success, we might just go down the hill a little bit and get some food there. But we'll see how that goes. So I guess that was that. So let's start with the first talk of today, which is Nicolas Regnault, if I didn't forget anything. Okay. Let's hope the switch works. Let's try. Okay, and Nicolas will talk about the structure of J states, if I remember correctly. Please.
Thanks. Okay, great. So, first of you, thank the organizer. I hope they will survive this 4 weeks reading all stuff. So, I think the aim of this talk is to discuss some results about the exact diagonalization. The exact diagonalization is a useful tool when you want to prove the fraction of quantum modifier. The usual stuff we do when we want to compare two quantum phases, the simplest thing we can do is to compute overlaps. The point is that sometimes overlap can be quite misleading, and I will show you one case which is related to the two-fifth fraction. We have two candidates. The J wave function here, the one can be from positive Family picture, in the Gaffney state, which have huge overlap and still have completely different physics. So if you want to, so we have huge overlap, and we will try to, when we ask the question, can we extract much more information from the ground state so that we can really see the difference between the two candidates. So the result I will show you basically have been done in collaboration with André Benedict and Duncan Haldane. I will show you also some previous results on the ambient entropy for more usual system like the Lofting wave function, which has been done with Matti Pasulaki and Sasha Suzuya. And maybe some disclaimer. So I have given quite a similar talk in Dresden. So if you were in Dresden, then you can know you have your access to the web. You can check your email and also interpret as you prefer. This is the outline of my talk. So I will give you a brief introduction, especially all the notation I will use in this talk. I will then show you all. To introduce the Gaffney, we can build it from different ways. And what is the difference between, you see how large are the overlap between the Gaffney and the composite Fermi state. Then I will show you this new tool which has been introduced by Lee and Haldane, which is called the entanglement spectrum. We'll try to squeeze out more information from the ground state to really see the excitation, some kind of signature of, the excitation of the state, and which are really signature of the physics we are looking at. And using this new tool, we will look back at the two-fifth state and see what are the common point of difference between these different candidates. And time to okay, so here we will be working the lowest Landau level. So let me just briefly remind you the notation, the lowest Landau level. So the one-body wave function are just some polynomial z, which z is the complex coordinate x plus iy of your electron, the power m, so m is the angular momentum times the Gaussian factor. So when you write down an n-body wave function projected in the lowest Landau level, this is just a polynomial in the z coordinate of your n electrons times some Gaussian weight that you can forget. We'll talk about the composition of this kind of n-body wave function on a given basis, which is this the usual n-body basis you can write down by Slater, using Slater determinant. So SL mu is the notation for the Slater determinant. Mu is the partition, which tells you the occupation of your states. And so, for example, here you got the Lofting wave function for two particles. So if you want to decompose on the Slater determinant basis, you will have two terms, namely this one and this one. And we will use the notation the notation for the occupation number, which is 1001, which means that you have one particle with angular momentum 0, one particle with angular momentum 3, and so we use only this notation of the blue box. And the other Slater determinant is the Z1 squared Z2 to the power 1 minus the permutation. So the notation will be 0, 1, 1, 0. So you will have plenty of this 1, 0, 1 everywhere, so just keep in mind what is the meaning of this notation. We will, of course, since we will talk about the two-fifth fraction, we know that the good description of the two-fifth fraction is given by the composite family picture. So you have your system with your electron and your flux quanta, and you do the transformation of binding to a flux quanta with to one electron. This is the composite fermion. And the good point is that you map the fractional quantum effect, which is a noun problem, of n-body into a simpler problem, which is just integer quantum Hall effect for this composite fermion. So if you require for this composite fermion to fill an integer number of Landau level, then you will end up with a fraction for the real electron, which is from P over 2P plus 1. And one example we will look at in particular in the two-fifth fraction, which means that you have two filled effective Landau levels. You can, this is more than just this picture. You can write down the wave function. So once you can write down, you can put it on the computer. You can compute energies. You can compute overlap with the ground set you can get from exact diagonalization. So it's really a powerful tool that we will use. So what about exact diagonalization? Exact diagonalization means that you will take a finite number of electrons and you will take some interaction which try to mimic the real system. The simplest one is just to take the Coulomb interaction. So remember, here you only work in the lowest Landau levels, so the Hamiltonian you have is just the interaction. So what you will do is to take this few number of particles and write down all the matrix elements, and then you will diagonalize this Hamiltonian. When you do that, you can have access to the spectrum, of course, whether the complete spectrum for small system size, or if you're maybe only interested in the low energy part, you can go to a larger number of particles. You can, of course, have access to the eigenstate. And when you have the eigenstate, you can compute various operator mean values, you can compute overlaps. But the main drawback of this technique is that this is limited to a very few number of particles. How many? Well, roughly from 10 to 20. Depends on the filling factor you're looking at. But don't remember that, well, to give a rough idea of the order on the system size you can reach, the good parameter is not the number of particles, but this is the size of the Hilbert space you have to deal with, which means also the size of the matrix you have to deal with. And roughly what we can do today is of the order of 1 billion of Hilbert space, including all the symmetry we can include. Another particular trick is that, well, you can look at your finite size system on different geometries. You can put it on a plane, but of course then you have all the nasty edge effect that you want to remove. You can do on a torus geometry, which is very powerful to probe the degeneracy of the ground state. Let's say the numerical equation a bit more tricky for the torus. So one easy geometry is a sphere geometry. So you really put your system in a sphere. The good point is that you have no boundaries anymore. You have simple one-body wave functions. You have two good quantum numbers, which is really great because you can take into account these two quantum numbers to characterize your state. You can reduce the Hilbert space you have in which you have to really work on. And the good point is when you look at incompressible states for the fractional quantum effect, they will have at least this property that the angular momentum is 0. The other good point is that the interaction is completely parameterized by a finite set of numbers, which are called the additive potentials. This is true for the two-body interactions. It is also true for the three-body interaction. You can decompose the interaction in the same way. It's also true for the four-body and so on. Another interesting point is the on the sphere, the relation between the number of particles and the number of flux quanta is not just given by the filling factor. You get this additional number, which is called the shift. And the shift is really some kind of signature of the state you're looking at. Meaning that you can have two different states that describe the same fraction, but when you put them on the sphere, they can occur at a different shift. Of course, if it occurs at a different shift, it really means that this is two different physical states. Okay, so much more technical slide. If you look at the decomposition of your state, just think about the Laplace wave function. So you decompose on the set-determinant basis. Many of the coefficients that occur in this decomposition are zeros. And this is not accidental. This is stemmed from the fact that the sum of the wave function are related to the so-called Jack polynomials, and they have this nice property that the only non-zero components are the one you can obtain from the squeezing. So let's look at the meaning of the squeezing. So one, you start with an highest weight, which means that you start with a given occupation of your Fock state. So let's start with the example, which is 1, 0, 0, 1, 0, 0, 1, and so on. So this is the root configuration, or the highest weight for the Laplace wave function. And then you do the squeezing. So what is the squeezing? Squeezing is just to make the one closer. So let's say you start with this kind of highest weight. Then what you can do is you can make this two one closer. It's always in one, right? You can't go on the other way. And you can repeat the procedure up to the end. If you do that, if you start with this configuration here, you will have 1, 2, 3, 4, I think 5 different states. So 5 different occupation numbers. This will, if you compare to the, imagine that the only constraint you have is the fact that your polynomial has a given total degree, it's a homogeneous polynomial, and so on. This constraint that all the coefficients has to come from the squeezing sequence really reduce you the size of the input space. It depends on the wave function you're looking at. But for the Laplace wave function, the typical reduction you get is of the order of 2. Okay, so now we have this reduced input space, and if you look for the homogeneous state, the state which have the angular momentum equal to 0, in some cases you will end up with only one state. This is true for the Laplace wave function, this is true for the movie and all the real state, and this comes from the fact that these polynomials are the so-called Jack polynomials. Okay, what are the Jack polynomials? Well, this is a mathematical definition for the Jack polynomials. So they are homogeneous symmetric polynomials. The eigenfunction of a particular operator, which is called the Laplace spectrum operator. They are indexed by a root partition, so or highest weight if you prefer, like this, and some rational coefficient alpha. In principle, so they are well defined for the symmetric polynomials, but since we are interested in fermionic states, so we have to go to the anti-symmetric wave function. This is just meaning that you take your Jack polynomial, which is j lambda alpha here, and you multiply by some just row factor in front, and this is the fermionic version of your Jack polynomials. And they have this nice property that when you decompose them on the set-determinant basis, you will have the only occupation number that will occur are the one that you get from the squeezing sequence. Well, of course, this Jack polynomials are the basis of the symmetric polynomials. So in principle, you can ask, okay, is it just changing from one basis, from the set-determinant of the symmetric polynomial basis to the Jack polynomial basis, so I don't get anything new. Well, the point is that in some of the most famous wave function, the fractional quantum effect, they can be expressed as a single Jack polynomial. And I will give you two examples here, which are the Laughlin wave function and the New-Read wave function. The good point is that if you want to compute this decomposition, for example, for the Laughlin wave function, you don't have to. Well, there is some formula, recursion formula, that will give you all the coefficients CU that appear in this wave function. Okay, so now let's go to the Gathian story. So there are many ways to build the Gathian state. We'll show you one. So before going to the Gathian, let's go back to the Pfaffian state. So the Pfaffian state is supposed to be a good description of the fraction 5/2 that appear in the experiments. There are many ways to write it down, and one way is to use this two colors approach. So you start with a group of n particles, which has to be even, and you divide it into two groups, and you paint half in blue and half in red, and you just create some Laughlin liquid with your red particle, another one for the blue particles, and then you symmetrize all the way to paint your particle in blue and red. To be much more precise, for the Fermionic wave function, we should start with the Halperin wave function, which is this one. Then you take the index to be 3, 3, and 1, so you get two Laughlin liquid at field factor 1/3, and you get the coupling between the two components. Then you symmetrize and you get the moving state. So this is when you start with a 3-3-1 wave function. If you don't want to start with another Halperin wave function, like the 3-3-2 wave function, if you compute the Fink factor, you should describe it that way. You describe the Fink factor, which is 2/5, which is the same one that you get for the chain state, for example. The problem here is that, well, since you have this 2 index, there is no easy way to symmetrize your wave function. And moreover, if you put your this wave function on this sphere, it will have a different shift from the one you expect from the chain state. So one way to fix this is to start with the Halperin wave function 332 and multiply by some permanent. So the permanent is like the determinants, but you remove the sign, the alternative sign you have in front. And so the matrix you have to consider here is 1/Zi red minus Zj blue. So now, once you multiply by this permanent, you can really symmetrize the wave function. And in fact, this will solve both problems. It's perfectly well defined to symmetrize the state. And moreover, the shift is now -4, exactly the same one for the chain state. So this state, when you symmetrize, is called the Gathian state. It has been proposed in 2007 by Cooper, Zay, and Simon. So in fact, this kind of set has it's a long story. It has been proposed, I think, at the end of the 80s, but also by Yoshioka, Jervin, and MacDonald. Even if it's not called the Gathian at that time. Okay. So there are other ways to derive the Gathian state. But first, the Gathian state is also a Jack polynomial. So you can get it just by doing the squeezing and so on. In fact, it can be derived from the root configuration, which is really close to the one you have for the Moore-Reed. So remember the Moore-Reed state, and this kind of root configuration. And so the Gathian is almost the same. So you have clustering of 1, and you add an extra 0. This is also, if you think about the Pinterest limit, people are aware of, this is exactly the same kind of pattern we have for the Pinterest limit. The other way to build the Gathian state is that this is the unique zero energy ground state of a given model free body interaction. Like for the Moore-Reed state, in fact. Well, the Moore-Reed state is also the unique zero energy ground state of another free body interaction. For the one for the Gathian, just a bit more complicated, but this is exactly the same kind of story. Of course, another point is that you can build it from CFT correlators, and we will talk about it later. Okay, so we have two-way function that describe the same filling factor and the same shift on the sphere. So you can really, since they have the same shift, you can really compute the overlap between the two, between the Jane state and the Gaffney state. And this is the result you obtain. So this is the number of particles, and this is the overlap, which is just defined as the. So this is the modulus. This scalar product. So sometimes you will have a 2 there, depending on the definition. But here I use this definition for the overlap. So in fractional quantum effect, we have also other candidate wave function for other fraction. And the most famous one is the Laughlin wave function. If you compare the Laughlin wave function to the ground state of the Coulomb interaction for the same filling factor, this is the kind of overlap you obtain. So this is for 14 particles. So the overlap is really it's pretty high. If you do the same kind of overlap calculation for the moving state, you compare to the exact ground state of the Coulomb interaction, the second order level, well, just minor points that you get with the interaction to maximize the overlap. This is the overlap you obtain, which is really lower than the one you obtain here. The size I've shown you here is for the Hilbert space is roughly the same size that you get for the larger system here. So it's really comparing the same story. Even the more particles not exactly the same.
Do you have roughly the Hilbert space size, which you said was 1?
Yeah, this one. Maybe I can go back in 2 slides. I will show you the numbers. So. This is not the only state. Well, this I'll show you the story for the 2/5 state, but you can write down the same kind of story for the other fraction of the Jane series. And if you look at, so it's the series is 2p over 2p plus 1. So 2/5 p equal to the 2/5 state. Three-seven state. And so if you hear this generalization, p equal to k, and so on. So if you look at other p numbers which are greater than 2, you can take this kind of wave function, which is really the trivial generalization of what I've shown you, and you can also compare with the Jane state of the same filling factor, and you get the number for the next fraction, 307, and the overlap are also pretty high. To be completely clear, the Hilbert space is a bit smaller here than the one I've shown you for the 2/5 case, because it's just a calculation a bit more harder. K equal 3, the wave function you built starting from K equal 3 here is, well, it's hard to say if it's exactly the non-unitary jack that has been proposed by Bernavik and Arley for K equal 3 and equal 4, but at least numerically it's very, very close. It's 0.9999 for a large system size. And in a recent paper, Steve Simon and Ed Reze has shown that this kind of wave function can also be built as the unique ground, zero energy ground state of a model for bond interaction. The story is just much more complicated than the case of the Gaffney. So the question is, we have 2 states, so the Jane have 2 states and the Gaffney. Do we capture the same physics? Well, the point is, I've told you that we can build the Gaffney state starting from some CFT. The bad point is that this CFT you have to use to get the Gaffney is non-unitary. So when you have non-unitary theory, the consequence is that you should get some critical state. Especially one consequence that the Berg theory is Gaffness, at least for the model interaction. And there is a strong reason to believe that this is physically meaningless. And your edge of the fractional quantum effect has to be protected from the Berg excitation in order to get incompressible state. And the other point is that the Gaussian state has excitation that obey non-abelian statistics, whereas for the case of the abelian, for the constituent picture, you get abelian excitations. Okay, so how two different states, such two different states, like the Gaussian and the CF state, can have large overlap. So let's look at other number. Maybe that there is some kind of signature you can get from exactization that will make the difference between the two. A simple tool is just to you compare your two candidate wave function, the Gaussian and the CF, to compare to them to the exact ground state of the Coulomb interaction, and you can an easy trick that we use quite often in the fractional quantum effects to change the short range component of the interaction. So you can make it stronger, which means this delta V1 is going to the large value. And the other way, you can decrease the short range component. This is an easy way, for example, to drive the system to phase transition. So if you did that for the 2/5 state, for 12 particles, so in red you get the overlap between the exact ground state Coulomb plus some delta V1 compared to the CF state. In green you get the same plot for the Gaussian state compared to the exact ground state and so on. And in blue you've got the gap of your system. And what you can see is that roughly both the Jane state and the Gaussian state behave in the same way compared to the exact ground state of the system. The overlap is quite flat until some point when it decreases and goes to 0, which is exactly the point where the gap of the system is closing. So we reach the phase transition. So this is for 12 particles. You get the same kind of result without the gap for 16 particles. Well, you get the same, really the same kind of behavior. Just as a reminder, here you get the same kind of plot for the moving state. If you do the moving state, I mean, it's got some kind of calculation for the moving state in the second order level and tune the V1 short range component interaction, then you will end up with this kind of plot for the overlap. So you will have a sharp, not a sharp, a peak region where the overlap is higher, and then it will drop. The red line here is just a reminder of what is the gap, the overlap for the Laughlin wave function for a similar system size. So it's really high. So you see that you will claim that if you look at this result, that there is no reason to discard the Gaussian state, and at least it behaved in a quite good way compared to the movement. Okay, so the question now is, what's wrong with the numerics? How two such different states can have large overlaps? First, well, when we do numerics, there's a one bad point when you come to n-body problems, is that you can't find the exponential. So, of course, the Hilbert space dimension will increase exponentially with the system size. So I've shown you some result for 12 particles. So this is where the Hilbert space dimension in which you are doing the exaggeration. This second number is if you were smart enough to take into account all the symmetries of your problem so that you can really reduce the Hilbert space as much as you can. You will end up with a dimension of 418. Now, I've shown you some result for 16 particles, so I think essentially will answer your question. So the Hilbert space dimension of in which you are doing the exaggeration is 155 millions. And if you take into account all the quantum numbers, of course, that you can't do numerically, but in principle they are there, this will reduce the Hilbert space to 70,000. So it's really a huge number. So there is one question is, since we have this trouble with the overlap, what is the meaning of the overlap? Well, I can easily tell you what is a bad overlap. An overlap of 0 is a bad overlap. In principle, that means that you have a wrong quantum number. So the two states you're comparing have different quantum numbers. The other definition of a bad overlap is if your overlap is of the order 1 of the square root of the dimension. So just imagine you're a monkey, you just type numbers and you get some random vector, and you can wonder what is the average overlap you will have between your candidate wave function and this random vector. So this is the order of the overlap. You have to be honest and take the dimension, including all the possible quantum numbers, right? So here, for example, you have to take this number and not this one, even if you are doing the exactization within this space. Still, if you look at this number here, the mean value for the overlap should be for the overlap between the candidate wave function and random vector should be of the order of 10 to the minus 3 or something like that. And the overlap I've shown you are really 0.95, for example. So it's really, the overlap we have obtained are really clearly different from this value. So, okay, so this is the definition of what is a bad overlap. So the question is, what is now a good overlap? Well, I have no answer about from, we think that the laughing wave function is a good description of what happened at the fraction 1/3. So I can use this, the overlap I obtained for the laughing wave function as a reference of what is a good overlap in the fractional quantum one effect. But as I've shown you here, the Moore-Reid state is supposed to be a really good description of what's occurring at phi half. Still, the overlap are really pretty small, definitely smaller than the one you obtained for the laughing wave function. So this kind of criterion, using the laughing wave function as some thumb rule to define what is a good overlap or not, is not, well, it's not really the good option. What is missing, in fact, to define what is a good overlap? Well, we should find a way to define how an overlap should scale with the system size, or how it decrease with the system size. If you take two different states and you increase the system size, the overlap is always decreasing. The question is how it should decrease with n so that you're preserving the physical property of the system. But even if you have such, if you can use such a law, which might be just comparing some power decay to some exponential decay, since you are only relying on few system size, going from 10 to 20, there is very few chance that you can see the difference between such behavior. So how we can try to overcome this problem of the exactization and let's say going beyond, trying to extract much more information. So there is two ways. First one is really looking at the excitations. Of course, in a perfect world, we should be able to compute the charge and statistics of the excitation in heuristic models. The problem is that this is completely out of range for the exactization studies. So the other way, and this has been done by Turk and Jane for the Gaffney state, is really to look at the overlap. So you will generate your quasi-Hopf by adding flux quantum to the system. And we know the excitation for the composite Fermi picture, the quasi-Hopf excitation for the composite Fermi picture. We know the excitation for the Gaffney state. And in both cases, this is not just a single state, this is really a subspace. And you can try to compare them by computing the overlap between the subspace you spread by the excitation in both cases. There is one drawback for this kind of study is that since you are dealing with quasi-Hopf and you're dealing also with degenerate state, you reach even smaller system sizes. Once again, you have the problem of defining what is a good overlap. And in that case, it's even harder to define the case of when you have spaces and not just a single state. So the question is, can we? It would be great just to look at the ground state and say, okay, we have two different physics just by computing some quantity. So is there a tool where we can extract much more information from the finite size studies of the ground state? And one tool which has been proposed by Alan is to look at the entanglement spectrum. So what is the entanglement spectrum? And before that, what is the entanglement entropy? So just pick up one ground state, non-degenerate. If you work on this sphere, the one-body wave function, in fact, it's like give you a natural partition of your system. So you can cut the system into two parts, A and B, in orbital space, which means that if you look at the occupation number, let's look at the, once again, the blocking wave function. So this is particle in a box, right? So you said that there is one electron for, so for the sphere, the index of your one-body wave function is the angular momentum. So I don't know exactly which is I understand. Okay, and so each of these one-body wave functions is like a small ring that will make the partition of your sphere. So cutting in the orbital space, which means that you will keep this part of these orbitals and trace out on this degree of freedom is really like doing the real space partition. So cutting this system in orbital space, you can compute the radius density matrix for the A part, just by tracing out on the degrees of freedom that make the B part. This is A. This is B. The radius density matrix you obtain that way is block diagonal with respect to two quantum numbers, which is the number of electrons you get in the A part, and the angular momentum of the electron in the A part. There is a natural quantity you can compute, which is the entanglement entropy, which is just the fundamental entropy for you can build from this radius density matrix. And there is this nice property like called topological state. You can extract, there is a subleading term which is really a universal constant that characterizes completely the excitation of your system. The point is, if you don't want to do that numerically, this is highly non-trivial, just because in the formula that says that the entanglement entropy should scale linearly to the size of the boundary minus this universal term, which is the topological entanglement entropy. This is true only for the thermodynamical limit. And so numerically, since we have access only to few system size, this is really an hard problem. And so Masudake and Sasha Suzuga and Kai and Salton have done the calculation for laughing wave function in UV, but I think it's pretty, all that has been done for the sphere geometry. But once again, we end up with a single number, right? It's like the overlap. And there is much more information in this reduced density matrix than just computing this number. So the idea of real only is to look at the entanglement spectrum, which means that we will plot the eigenvalues, well, minus log of the eigenvalues of the reduced density matrix as a function of one of the quantum number, which is the angular momentum of the A part, while keeping the number of particles fixed in this case. So now if you do that, this is the kind of plot you obtain. So remember, this is the minus log of the eigenvalues of the reduced density matrix. So this is the angular momentum of the particle in the A part. And this is the spectrum you obtain for the Laughlin wave function, 13 particles. This is the number of orbitals, the number of boxes you have. Well, up to number 1. Okay. And you cut your system really into two equal parts. So this is the initial cut. And you require to have 6 particles in the upper part of your sphere. And this, so you end up with this result for the Laughlin wave function. In fact, this shape with all the states ending up in the tail here, just ending up with one state with maximum angular momentum, is this kind of shape is true for all the Jack states. So just to be more precise, what you are doing is, in fact, you are doing the split decomposition of your ground state. This means that you will cut your system into two parts, A and B, and the weight you've got in front of this decomposition is just related to the eigenvalues which are shown here in the plot. If you want to do this decomposition, that's why I was talking about decomposition of Fock space, you really need this information. You need to do the decomposition of your ground state on the Fock basis. To do this kind of calculation, you need to cut your system in the orbital space. And if you think this is a trivial task, and the answer is really no, even for the Laughlin wave function, there is no known formula for. So remember that the wave function can be decomposed on the zeta determinant basis, right? So this coefficient, knowing this coefficient for even for the Laughlin wave function, which is really the simplest one you can imagine, is an hard mathematical problem. The best formula we know up to now is a recursion formula for the CMU. But still, all the Jack polynomials have the same kind of entanglement spectrum with this shape, which end up with the tail and only a single state, so only a single. What's this one? Only a single state here at the maximum LZ value. The maximum LZ value you get here is the one you can expect if you see that you cut your system into two parts. So your original system is on the sphere, you cut it into two. So roughly speaking, you end up with two disks. And the maximum LZ value you obtain, you see here, is exactly the LZ value you should obtain for the same wave function, but on the disk. The number of particles, which is the number of particles you have kept for the A part. The other great point is that the low energy part of the spectrum, so what I call the low energy part is in fact this part which is here, which is the part which has the most weight, most important weight in the resistance matrix. Remember, this is minus log. So the important part of the spectrum is here. Here, this is the high energy state you don't care about.
How do you define the cut?
Between what is important?
Low and high.
So there is, for this model wave function, there is one which is when you start having finite size effect. So when you you see that the counting of this low energy part here, the counting you have here 1, 1, 2, 3, and 5. This is the counting you expect for the edge mode of the Laughlin wave function. At some point, since you have a finite size disk, you will start missing out this edge mode. So this is defining what is the low energy part of your system. The other way is to look at when you look at the Coulomb state, Coulomb interaction state, and you do the same kind of plot. Then you can also define what is the low energy part of the energy. I think that, well, to be completely honest, this is still one of the problems of defining the scale of this system. But I will talk about it later. Okay, so this was the counting I've shown you for the Laughlin wave function. It's really counting you can for the edge mode of the Laughlin wave function. So the counting was 1, 1, 2, and well, the edge mode, well, for the disk we have the ground state. Then the first edge mode you can build is the Laughlin wave function times the sum of the z high, which is the coordinate of your electron. And if you look at the next edge mode you can build, you have these two possible ways, namely the Laughlin wave function times the sum of the zi squared and the Laughlin wave function times the sum of I from j, zi, zj. I think I will skip this one, but just to briefly summarize this into next slide. You can, in fact, for the Jack state, you can really prove mathematically that you have only one state for the maximum LZ value. And in fact, you can for the model wave function and the Laughlin wave function, you can really prove the counting you have. But it's really highly non-trivial that the counting you have here, 1, 1, 2, and so on. Imagine that this is a huge matrix that you have diagonalized. You don't see the reason why you should get this kind of counting apart from the argument that you should mimic this geometry. In fact, for all this model wave function, you can really prove that the counting you obtain here is really the counting of the H wave. So we'll skip this part. So just some to mention that if you're interested, there is we have a Jack generator. If you also want to get the decomposition of the Jack wave function, there is this website here. And if you want to see much more taken on spectrum, we have also a web page where we have thousands of taken on spectrum that you can look at. Okay, so now the question is, this was for the model wave function, a simple model wave function, the Laughlin wave function. What's happening when you look at more realistic system? So you take the Kuhn interaction and you compute the ground state for the same field factor of the Laughlin wave function, and you compute the entanglement spectrum. This is what you will obtain. So this is, as a reminder, you got the entanglement spectrum for the Laughlin wave function, the same number of particles, the same cut, and so on. And you see that you will find back the same feature that you have for the Laughlin wave function with the same counting and so on. Of course, since this is no more a model wave function, you have some higher energy states. And the higher energy part is somehow not protected, but it is separated from this low energy part by some entanglement gap. You can, of course, define different entanglement gap depending on which LZA value you're looking at. But up to the finite size effect, what you can see is if you take not the pool interaction, but the pool interaction plus some short-range component, or remove some short-range component to drive the system to a phase transition, you can see that the entanglement gap will close when you drive the system to the phase transition. So this is the result you have here. Forget about the black dot, just focus on the purple one. The purple one is really the entanglement gap. As a function of the short-range component you remove. And you see that at this point where the system is no more incompressible state, this gap is closing. So even if it's not clear, at at least from my point of view, I can't tell you what should be a good entanglement gap. Should be 7 or 3.5 or whatever. But at least the feature that this somehow characterize whether, if you're still in the same quantum phase, one signature that this is a good description is, I think, it's really related to the fact that if you drive the system to a phase transition, this gap will close. Okay, so now let's look at the two-phase state. So first, let me tell you that if you want to compute this entanglement spectrum for some states which are not some Jack polynomial, this is really a hard problem. Basically, there are many ways. Well, there are some ways to get this decomposition. Whether the state is a unique ground state of a model Hamiltonian, then you can just use exact diagonalization. The ground state will be the state you want to look at. And since exact diagonalization is working in this basis, you directly get the decomposition. Whether this is a unique Jack polynomials, and we have this recursion formula. But now, if you, for example, if you want to look at the Jane state, the story is much more tricky because there is formula is when you do the projection is much more tricky than just the Laughlin wave function, for example. And there is no known exact Hamiltonian for which, for example, the Jane state would be the unique exact ground state. So, but another way to overcome this problem is that in the case of the Jane state, you can look at the clustering properties, and what you can show is that the chain state, at least for 2/5, simplest case, can be built from this root configuration. So if you compare to the so this is the root configuration for the Gaffney, so for 6 particles. And now let's look at the CF state. So the boundary are the same. You just make the one step outward. So this is the root configuration for the composite fermion state of 2/5. So you see that if you do one squeezing, you will end up with the Gaffney root configuration. So in principle, when you are looking at L equal to 0 state within the subspace, from the squeeze subspace starting from this root configuration, you will also get the Gaffney. So that's the major difference between the Jane state and what I've shown you for all the Jack polynomials. For the simple wave function I've shown you, is that this root configuration, when you look for the L equal to 0 state, this will not be a single state, but this will be a subspace. For example, for 16 particles, you will end up with 4 states. The point is that the Jane state lie exactly within the subspace. If you wonder if there is anything special about the Jane state within the subspace, you can, for example, compute the overlap. So you take each point of your subspace, or at least a discrete version of your subspace, and you compute the overlap with each point with the exact Coulomb interaction, and you end up with this kind of plot. So this is the 2 parameters which will define your subspace, and in color you got the overlap. The Gaffnian state is this white dot here, and the cross here is the Jane state, and the yellow part is the overlap, which is the highest value. So the Jane state will be close to the maximum, to the value which maximizes the overlap within the subspace. This is not exactly the one maximum overlap, but it's really close. The other points, as well, there's another property of the Jane state in this subspace. So okay, so now using this trick that the Jane state lie within the subspace, what you can do is to compute the component, the decomposition of the Jane state within the subspace using Monte Carlo integration. The point is that if you want to do that directly using scatter determinants, this is a huge basis. You will have Monte Carlo error for each component, and at the end you will get just some garbage stuff. Since here you have really small Hilbert space of 4 states for 16 particles, you can really still use the Monte Carlo integration to compute the decomposition of your state. Okay, so let's look at the 2/5 state. So in blue here, for the left part, this is the entanglement spectrum for the Gaffney. So you see that the Gaffney is a bit more messy than the Jane states. The counting is this one, so it's 1, 1, 3, and so on. So this scalar calculation is done for the hemisphere cut, 16 particle. And this is the same, the entanglement spectrum for the Jane state, the same number of particles. So if you look at what is below 8, right? So this is the minus 1 of the eigenvalues of the reducing symmetries. So what is below this line here is really the same that you want for the Gaffney state. So you can wonder, well, since you have a huge overlap, it's quite normal to get such a sigma entanglement spectrum. Well, the answer is it's not that obvious. You can build some example where you get 2 states which with different entanglement spectrum, but still high overlap. Okay, so this is comparing the Gaffney and the Jane state. Now, if you look at the edge mode of, well, if you do the counting for the Jane state, well, if you start including some state higher in energy, the counting is a bit different. So it's 1, 2, and 5. So you can wonder what is the reason for this 5. Well, if you take the Coulomb interaction, this will really clearly show that this is the right counting you should take into account. And in fact, this is the counting 1 to 5 is exactly the counting you can expect from the chain state, where you get basically 2 copies of U1, since you have your 2 render levels. So this is a pretty nice story that's starting from all the wave function, which is not a jagged polynomials, that you can do the counting of the edge for such a state. So that proves that this counting continues to work. I mean, this counting works beyond the jagged state, and also that the I overlap is not accidental. Okay, so now let's take the Coulomb interaction, ground state, and see and try to compare with the previous results. So in blue, you have the part of the spectrum which is really close to the one of the Gaffney. If you start including the green part here, you really match the same state, I mean the one in the chain. And yeah, you can also compute the entanglement gap for this state. So starting from here, for example, to the I energy state, or this one to the I energy, and see what's happening when you drive the system to a phase transition, they close and so on. And the answer is yes. And once again, the counting, of course, there is a question of where you should put the separation. There is one way to also see that is you see that, well, the way we obtain the chain state decomposition is by using vertical integration. So you can really start moving a little bit away from the chain state and see all the entanglement gap is changing. And this, if you stay close to the chain state, you will really see the structure 1 to 5 will stay fixed. So this is the result for the entanglement gap. So here you've got, as a reminder, the overlap of the chain state and the Gaffney state compared to the Coulomb interaction plus some short-range components. Now you get the entanglement gap. So let's just focus on this one. Entanglement gap between this state here and the high energy state, so the one with the highest angular momentum. And oops. So this is the entanglement gap, and well, the system close something change from incompressible state to compressible state in this region, and you see that the overlap is really the entanglement gap is really pretty
Sorry,
flat.
I thought you defined your entanglement gap to be the lowest, not in the second lowest.
So there is
It's different. Quite different.
okay. So there are many ways to define. You can define different entanglement gap. So there is one natural way, which is just take the state. There's a natural state which is corresponds to the maximum LZ value, right? So you can define the first entanglement gap here, right? Then, of course, since the counting is different for both the chain state and so the plot I've shown you here. In red, this is this gap, right? In red, you get the entanglement gap.
That's the low.
That's the lower. Yeah, there is two things you can compute. You can compute the entanglement gap. And the other way is to, well, here you get eigenvalues, but you have also an eigenstate of your distance matrix attached to these eigenvalues. And you can track all this state here is changing when you change when you drive the system to a phase transition. So this is the green curve you get here. So roughly speaking, what you will say is that this state, since this is the one which represents your system on the disk, or on the ground state on the disk, you can see that this state barely change when you tweak the interaction, and that it will drop as soon as we drive the system to a phase transition. here you got also many other plots for the other entanglement gap you can define. So for example, here, the main plot is the gap between the gaffing state and the high energy state. And the inset you have here is the gap between the states which you take into account when you look at the counting of the Jane state. The counting of the gap is 1, 1, 2, 3. The counting of the Jane state is 1, 2, 5. So you can define two entanglement gaps depending on whether you look at the Jane state or the gapping state. So the main plot here is for the delta 1, which is the entanglement gap between the gapping state and the high energy state. And the inset here is the same kind of calculation for this other gap. And the point is that the only difference between these two gaps here is that the gap between the Jane state and the high energy state above seems to close faster than the one you get for the gap.
But sorry, I missed. The delta you wrote there, was that in common for the Gaussian and the Jane?
Well, since they don't have the same counting for both the gap and the Jane state, as soon as you look at the excitation, then you can define two different entanglement gaps.
Oh, so that was only for the Gaussian.
So delta 1 is for the Gaffney, because the Gaffney has the counting.
I mean, the red delta was for
the first one.
Yeah.
The first one, well, there is only one state both in the Jane state. Well, for the Gaffnian.
That's what was my original question. Is that the same?
Well, for the Gaffnian, so this is the spectrum for the Gaffney. So you can, yeah, this is the same.
You cannot distinguish.
No.
Okay.
Well, of course, you can claim that this high energy state is also a part of the Jane state, right? But since this one is really, I mean, remember this is exponential minus 14, so it's really a small component of your reducing matrix. So you claim that the low energy part is really, at least in this sector, is really this state here, which is exactly the same.
Sorry, that's what's confusing me, is you keep pointing to that one, but that's the second highest low. I mean, the counting 1, 2 comes from the lower.
The counting, so the counting 1, for the Gaffney, the counting is 1, 1, 3, right? Now, for the Jane state, the counting you have is 1, and then there is another state which is here. This is where the two spectra start to be doing different. Okay, some high energy states somehow are present in the Jane state and are not present in the Gaffney.
But it's not so easy to see that it's 1, 2, 5 from this,
no,
or is it?
No.
But there are extra states where they.
So the 1, 2 is, well, it's pretty clear, right? 1, 2.
2, maybe.
Okay. So the question of 5 is much more tricky. There are many ways to see that this is 5. The first one is to compare with the Coulomb interaction, where the gap is pretty clearer. The counting 5 is much more clearer for the gap in the Coulomb case. The other way is to say that, well, the way you obtain the Jane state decomposition, right, is by picking up one state in this subspace of four degenerate states, right, the way you build it. So since this is Monte Carlo integration and you get some error, you can prove what is around the Jane state, or what you should assume to be the Jane state. It's like, well, imagine you have a two-dimensional space with it. So, which are your two vectors. So the way you compute the two components using Monte Carlo integration. So you have some error for both components. So what you can do is to compute the same spectrum by slightly changing the component, and see what's happening to the integral gap, for example. If this is still what is robust to this small change. And you see that the counting you have 1 to 5 counting is robust against these small changes. it's time to conclude. So I think that the main message here is one has to be careful when we deal with the overlap. I think that the good point with the story of the gap is to show you that you can have huge overlap between two ground states and still having two different physics. Still, this is an interesting question of what is the relation between the Gaffney state and the composite frame picture. Or you can, well, I mean, or you can go from this finite size system where you want to do the same, but physics is completely different. So how you can try to probe your system to make the difference between the two. And at least the antagonist spectrum offer a way just by looking at the ground state. Another non-trivial result is that the edge mode counting, it was, I mean, the fact that the edge mode counting on the antagonist spectrum is working fine is only true for the Jack state, mathematically. It seems to work also for some non-trivial state like the Jane state where we don't have this nice formula for obtaining the CU coefficients. I think it's really non-trivial. And well, I think this really we will, of course, to be a complete benchmark to compare two different states. There is many steps that we should try to overcome. The first one is maybe trying to have a better understanding what is an entanglement gap. All the entanglement gap is protecting the physical property of your system. This was the question Rasa asked. What is the meaning of the entanglement gap? It's a number. So what is the meaning of 7, for example, for this? So one way maybe is to, if we can compute the entanglement spectrum for some model wave function with one parameter, then we have a complete control and know exactly in which phase we are, then this might be an option to really try to understand the exact meaning of this entanglement gap. I think that, well, from the point of view of the Jane state compared to the Gaffney, I think it's the similarity between the two states, at least for the ground state, is really quite fuzzy. We should really try to dig at more to understand what's happening. For example, there is a question of how the CF approach builds somehow the problem of the Gaffney state. It's all addressed, partially addressed by Thierry in some language. And also there is another question which related to the paper of Steve Simon and Eder Rezai that's been in comment last week. So if you look at the two-body interaction for all this series of functions, it seems to favor the non-unitary state, which is pretty bad from the CFT point of view. So I think that there is also something here to understand why we have such a property for the model.
Don't you mean that they favor the unitary state?
Well, if you look at the plot they have, right? So they have an extra parameter which basically allows you to span different CFT theory. And they look at the overlap between the so boson, right? But the story is pretty much the same for the framework. So if you look at the overlap between the exact ground state of delta interaction for boson and the ground state of their Hamiltonian they have, where we have one parameter which can relate to the central charge of your theory, you will see that the maximum of the overlap is close to, it's in the region where you have non-unitary CFT. They have different, they have also some, they have some unitary CFT, right? But the unitary CFT have bad overlap with the ground state of the delta interaction. Okay, so that's pretty. So if you're interested in a reference, this is the paper you can find the result for the entanglement spectrum, paper about getting this coefficient here, and they want to studying the phase transition using the result. Of course, you have all the data here, and that's pretty to say. Thank you for your attention.
We have already had questions, so let's just keep on discussing. We'll get tired of it, others can just leave whenever they want, I guess. Yes, Hans was first.
This last thing you said, that is assuming that the wave function is just one conformal block then. No, but I mean the 2/5. You can write it as the 2/5 with, you know, with the gain wave function purpose, and you can write them as sums of conformal blocks. So that last statement couldn't include that.
That statement seems to favor the Gaffney at 2/5, but that's not, is that their conclusion or?
Well, I'm not sure to take the question, so...
No, but I mean the Jane state, the 2/5,
Right.
is a good, that's a good state.
Right, I think that no one will claim that this is not...
Yeah, but that
But
is
it's
given
unity.
as sums of conformal blocks for, you know, unitary CFDs.
Right.
Question is, how does the Jane state fit
Well,
in that statement?
Yeah.
Not at all, I guess, because, I mean, the statement, I mean, Simon and Reza, they have different CFDs, like this S3 CFDs,
Yeah, so,
that they have a common about, so.
yeah, that's, if you want to write down this thing, the wave function is CFT only from primary field, it's the standard.
Yeah.
Then you end up with picking up the unitary one.
Yeah,
Okay.
That's
what.
In fact, I have a question which is perhaps related. So, you know, if I think from the point of view of Hamiltonian, okay, for which Gaussian is the exact ground state, is there a way to see from that Hamiltonian that this would be a gapless state in the thermodynamic? It seems to be perfectly valid.
So there's the question of if numerically this gap, the gap of the free body interaction, will go to zero. Well, there is no published data on that. I can tell you the data I heard from. So Juanito Male has done some calculation up to 14 particles. Well, it seems too close. It's well, there's a problem of doing the finite size scaling for the gap. But if you do the calculation up to 14 particles and you plot them and try to look if it goes to zero, it seems to go to zero. But there is no published data on that.
And how about the entanglement gap? I mean, you showed that for 1/3 it vanishes when the system goes through a phase transition.
Right. So the
What happens to the entanglement gap?
entanglement gap is staying constant.
As a function of the number of particles.
Well, roughly, yeah.
So you don't see any evidence for its becoming a critical state.
No. Well, if you just look at so you extract the Gaffney part of the Coulomb interaction, you compute the various gap. At least for the one which is associated to the maximum angular momentum value. This one seems to vanish. This is roughly there was the first paper by Lee and Alden gap for movie state, and it also seems to be quite constant even if you increase the system size. For the Gaffney here, we go up to 16 particles, which is the best system size you can do for interaction. There is no sign of closing the entanglement.
Very naive question, but you were saying that for these Jack polynomial-like states, the entanglement spectrum always has this banana shape, right?
Right.
And then if you start looking at states that come from Coulomb interaction, you get something that looks like superposition of multiple bananas.
Right.
Right. But if you look at the actual Gaffney state,
The shape is a bit different.
already looks like there are two bananas. So
Right. Right. The point is that you can. Let's see. The counting here, I mean, you can really prove that you have this decomposition for the Gaffney state. This is not that you have only one state here and one here and so on. Well.
there's
So
no
of course you can
indentation.
claim that you have a superposition of this guy here and this guy here.
Right, yeah, it looks like there's some kind of structure there, maybe it has a physical interpretation, but maybe it doesn't.
The point is, what I mean, both if you take the regnault state or the Gaffney's, the maximum LZ value you should expect this picture with 30 cm to get to disk. This is the value you should expect. So then it will get why you should.
There's no particular reason why there should be such high weight in states that.
No, but the point is the well, the weight is also it depends on the geometry of the working. There are you can express your wave function in different well, you can do it on the disk and cut this thing on the disk and you will get different weights. For example, you can forget about the geometry. You can write down state in so-called normalized spaces for the condition of the geometry, and then you get the another shape. It's still a counting as
But maybe the point is that you still sleep in the non-unitarity, because if you have banana shape, your lowest state is highest angular momentum, lowest energy.
let's see for well here of course this one is the
Yeah.
highest weight, right?
But,
For the Murid state, I'm not sure that maybe you have some state which is have the highest weight, which is an highest weight, and still is not the maximum. I think so. So the fact that this is the one with here for the lawful state, the fact that this one, the one with the maximum LZ value, is the one which has the highest weight. I think this is completely acceptable. This is not really the fact that it's a unitary CFT.
You don't happen to have comparison between the Fafnian and the exact 5-hat state for
Well, they
Okay,
have
entanglement.
some data in the paper by Ian Haldane. The original
Okay,
paper
they have-
introduced the impedance spectrum. They have looked in fact at the case of Fafnian state. Or if you go to the website, I'm showing you there all the data for Fafnian crew interaction, the defect crew interaction. So you can really compare.
Other questions? If not, let's thank Nicola again.